So welcome everybody. Today's seminar is called Before and After Submitting Octave and Matlab Jobs on the Clusters. Now, I'll be using examples of running Octave, but the general strategies that I'm talking about relate to pretty much all packages. The focus is really on describing sort of a way of easing the process of moving from your local machine and doing the required work before doing a large set of production runs to jobs. So these are basically ways of facilitating the management of files between your local machine and your remote machine, how to keep track of them in a very intuitive way, and then doing things like either running your scripts locally and then replicating it interactively on a compute node, or visualizing it through a VBI node on the system. So we give an example in this presentation about a certain process on an example data set that I have. Run it locally, visualize it locally, move it over to the cluster, work with it interactive on a compute node there, and then do some profiling on the process in the compute node, and then visualizing some of the outputs through a VDI node on the remote cluster. Okay, so I'm going to get started with an overview here. So the initial thing that we'll do is we'll talk about the compute cluster, basically the layout of what resources are available in the Compute Canada compute clusters and how they're accessed. Then I'll talk about working with Octave locally. There's a example process called the mean subtraction. We'll visualize the data and the output, and then we'll profile it. That's all done locally. The next thing we'll do is mount a remote drive and explore the files that we're moving back and forth between the two systems using the meld software. And then we'll mount the drive with SSHFS. And then next we'll work interactively and do profiling on the actual compute clusters that we want to test the performance of on the system itself. And then we'll also do visualizing remotely. Then sort of the last step that we want to do on interacting with the data is actually submitting a bunch of jobs that will do the profiling themselves. So this will include functions for capturing the performance of the data in the actual jobs. Not something that we really want to maintain in production because they can introduce extra inefficiencies. But what we can do is we can capture a bunch of parameters of different runs doing that. And then finally, we'll do the actual visualization of some outputs that came out of the jobs that we're doing the profiling, and then check that the output doesn't change across different attempts or runs. I'll just start off with this overview. I'll probably come back to this diagram a couple of times during the talk. What it shows is basically the relationship between the laptop that I'm working on right now in my home office and I'm presenting on, but I'll also be performing the various analyses. So typically whenever we do production work, we SSH to a login node, and then this over here is the cluster itself. I'll be using Graham today. So we go from here with SSH, we go over to the login node, and then we have a terminal here. And then on the cluster, we have the login node where we end up, but we want to do all of our large-scale production work on these compute nodes over here. And the way that we do that in production is we just send a bunch of jobs using sbatch, and then those get distributed to the compute nodes as we have access and we're at the right priority. So that is basically the goal of most of the work that's happening on the cluster. Is all of the researchers in Canada are submitting all of these sbatch jobs, and all of the compute nodes are running production work. And ideally, they are returning the results that we want in the most efficient way possible. But what today's presentation is about is mostly things that we do sort of before we get into that production work. So some of the things that we'll do this time. So I have basically my home directory on my laptop over here. And then we have different file systems on the compute cluster. And what I want to do is actually use the data transfer node, another node that's on the cluster, and mount some of the file systems back and forth between my local computer and the remote computer. That will allow me to use software on my local computer to monitor what new files exist, for example, job output files or new output files that I'm generating in my interactive instances. And in fact, I can then use a local instance of Octave or Matlab to visualize those outputs. So that's what I'll do. That's what I'll demonstrate in terms of just being able to monitor interactively the relationship between a local directory and a remote directory, or in fact, multiple remote directories. What is the next thing? The next thing that I do is in a local terminal, I'll go to a login node. And then what I want to do is run the procedures that I've been testing on my local machine, but see how they perform on an actual compute node that I want to do my production runs on. So in the past, on previous systems in SharkNet, we had development nodes. These were specific nodes that you would log into and you work with. But on the new systems with Slurm, what we do is instead of submitting a bunch of sbatch jobs, we can submit jobs to Slurm with salloc or Slurm allocate, which will put us on a compute node, just like the batch jobs end up, except now we'll be there interactively. So our terminal will actually go from the login node down to the compute node, and then that's where we can work interactively. So what I'm going to do is I'm going to test a process on my local machine. I'll go over here, do an interactive job, and then I will replicate the profiling in that compute environment that I then want to use for the production runs. This is sort of an ideal situation, because what we can do is whenever we submit the salloc jobs, we can request the various types of resources that are available on the compute nodes, and basically test in production the different ways that we want to then run in production. And then, so after that, the next thing that I'll do is once I've tested interactively on here, I will then make a function that I will then submit test jobs interactively that will generate the output profiling information that I want. That will, as close as possible, replicate the process that I want to do in production, except it will collect profiling information and generate output that I want to then explore the process. And then finally, whenever I want to actually interact and do visualization on the output of those test jobs, what I'll do is I'll use Tiger VNC from my local machine and then go back and forth with another type of node, and that's the VDI node. In the VDI node, basically get an interactive visual desktop. And from there, what I'll do is I'll open the Octave integrated development environment, and then I'll take a look at the output plotting results. So I've made some data available. I'll show you where it is after, but the data is from my research that I continue to do in behavioral neuroscience, where we look at EEG data, which is the electrical signals from the scalp. So this example data, there's 120 electrodes on a human scalp, and we record voltage values every millisecond or so over the duration where the individual does different cognitive or behavioral tasks. And then we analyze the brain signals that propagate through the skull. So there's a whole bunch, and this field is pretty much largely bound to Matlab, and several packages are developed in Matlab to do this. So that's why I'm using that example. So here's basically the example of what I want to, the computational example that I'm running today. So what we have is a three-dimensional array whenever we do EEG research, where we see this is a single signal over a short period of time. These are just voltages of the scalp. And then what we actually have is multiple signals. So here's an example of about 35 of the signals over a period of time that way. And then what we see is that each signal is substantially different from the other one. That's why they look so jagged, and we can't actually see any of the variability across that dimension. So what we need to do is we need to basically run a mean subtraction where we center all of these lines at 0. And then that's when this data looks like this, and we can start to interpret. So it's basically an initial, rebasing of the signal. So that computation for subtracting the mean is basically what I'm looking at in this. And then what we want to do is just make sure that we're always ending up with the same result that we have here. So there's multiple ways in Matlab of doing this. And often what happens whenever I'm starting a new study or consulting to a group that's doing this kind of research, there'll be some code that I get access to, and then we never know exactly how this computation was performed. And in the sort of the worst case scenario, what's happening is there is an element by element looping through multiple dimensions. In this case, by default, somebody just might write out explicitly that they'll loop through all of the rows, then they'll loop through all of the pages, and then they'll calculate basically the mean across the columns on every instance, and then subtract that. So they basically go all the way through here, all the way through there, performing a mean and a subtraction every time. And that's substantially more computations than we need to do. And what we want to do is basically find out if this is happening in a piece of code. Then a better way of doing it is just changing that to basically loop through only the rows, or sorry, loop through just the columns, and then calculate the mean, and then subtract it from the two-dimensional array. That's basically rows of pages. Or better yet, just because it's the same mean every time, calculate the mean, and then just go through all the columns and subtract that two-dimensional array from all of them. And then even better is to just calculate the mean once, extend it to a three-dimensional array, and then just subtract those two arrays. Or what's even simpler, and now in more recent versions of everything, just broadcast. So we calculate the average, in this case, the average column, and then we just expand that off in a single subtraction. So what we're going to look at is basically how to profile these different methods and determine which way is the right way of doing it locally, and then I'll go do it on the cluster. Okay, so as I talked about before, there's a GitHub repo here, and you can grab the functions and the data that I'll be using in this presentation anytime just by running this git clone locally or over on the remote. So actually, the first thing that I'll do is I'm just going to open I'll just open my local instance of Octave over here. And I'll just run this brief command to give you a view of what I'm doing. Okay. So here's Octave, and what I'm going to do is I'm just going to go into this demo folder. I'm sure I remember where I put it here. Excellent. Okay. There we go. Okay, so we have here is just the directory. Sorry, back up. So in this directory, I can basically just load the data set once this has been cloned down, and then I can just run the plot, a single channel, which will give me this single channel over time. And then what I want to do is plot the surface. I get the next one, which is the unmeaned, and then finally do the baseline subtraction. So in these three commands, I can basically get the final example of what I want to generate in the various places. And let's close these. Okay. And then in this example, you can basically run two different tests. So this is the loop through the rows and columns, and then the mean subtraction. That's just taking a single column and then comparing the two results to make sure that everything ends up being zero. This zero comparison basically just makes sure that if we run it a bunch of different ways, that we're always getting the same results. As well, what I can do is, if I'm concerned that remote execution is giving a different result than my local execution, then I can also check those back and forth, as long as I can access both directories from wherever I'm visualizing the data. Okay, so the next thing that I want to do is just take a look at the profiling of the function. So if I'm in my Octave instance, what I can do is I can say, I want to turn on a profiler, and I'll clear the data. I'll turn the profiler on, could do a TikTok and run an example, and then take a look at the actual profiling information data. And this is what ideally we always do every time we get a new piece of procedure or a code from another lab, or even something that we did a while back. You want to test how it's performing. So I'll do this example here. Let's bring Octave back. So now what I'll do is I will just take this example where I load the data, and I'll run the TikTok, and this will loop through and perform the mean subtraction, which it's doing now. Run. See that this one is going through a whole bunch of stuff. This one actually took 13 seconds to run, and then we end up having this profiler information. Now, what I can do from here is I can do prof view. So, I think that's actually prof show. And then we can see here that what ends up happening is the code ends up spending 65% of its time in a mean operation that it's running 32,000 times. So the issue is that what we want to do is reduce the number of times that it's calling where it's spending the most amount of time. Ideally, in something like Octave and Matlab, we can reduce the code to really just running these binary calls and not doing these high-level functions over and over again. So the next thing that I can do here is run a separate example where I'm reducing the number of calls by simply copying or In this case, just calculating the mean once, looping through the columns, and then subtracting that mean from the columns. And in this case, we're now down from 13 seconds to 0.16. And then if I do prop show, we see here that basically we've kind of achieved what we wanted to do, in that it's spending 60% of its time, and that's where it's spending the most time, in a binary subtraction that it does 256 times. So what we've done here is basically just determine that the way that we want to do it is this second method, and there are other methods of doing it. But here locally, we've determined that this is right now the best way of doing this on my local machine. Now, with that, what we can do is we can then move over to the cluster and start doing the same thing. So what I'm going to do here is I'm going to basically start setting up my environment to work intuitively on the cluster, keeping track of files that I have locally and remotely. And there's multiple ways of doing this, but what I'm going to do is I'm going to basically copy the directory that I'm currently working from locally. So I have my desktop repost 2023 demo here. And then what I want to do is, in this case, I've copied it over using the data transfer node. So I've copied it over using the data transfer node. I put a copy in Scratch, and then I put another copy in project. And this is basically just for a demonstration. What I'll do oftentimes in a new study is I'll have a copy both in Scratch and in project, and then I'll basically always just bring things out of Scratch, keep the copies while the project is active in project, and then only leave what I need in the Scratch directory. Now, what do I have here? So then I'm just basically making 2 mount points in my directory, a place where I'm going to mount the local drives to my local machine. And then here I'm using SSHFS to mount both of those directories into my local mount points. And then lastly, what I'm doing is I'm using a program called Meld. And then this allows me to basically view my local folders, the folders that are in Scratch, and then the folders that are in project. And then as I run things from different directories, what we'll do is we'll see these updating. For example, if I run in Scratch, those files will appear there. If I start modifying the functions that I have in the remote, then we'll also see that these are different between the 2 or the 3 directories. So once I have the directories created over there and I've taken a look, then what I can do is start working interactively on the remote machine. To do that, I'll demonstrate basically SSHing over, going to the example code that I have there, loading Matlab on the remote system, and then starting an interactive job with salloc. What will happen with salloc, I have the example here, basically the notebook or the terminal will go to a remote or a compute node, and then I can work interactively on that. And then once there, I can do the exact same thing. So this code here is now the same code that I was running locally, and then I can test the profiling information that happened on the compute node. So once I've tested it interactively, what I can start doing then is submitting these jobs or submitting the actual process as a batch job. So not interactively, but I can submit a whole bunch of these jobs in parallel to test a bunch of different parameters that I want to test out, and then save those outputs that I can then look at either on my local machine or remotely. So this example basically goes over that, where I now create a submit script. And that submit script ends with the execution of Octave running this sub-m repmat function that I created over there. Submit the function by giving it SRID, and then I can check on the state of that job. Now, basically, the function that I've created is listed over here. It basically takes inputs. It starts the performance evaluation, then it performs the function that we've already looked at. It terminates the profiling, and then here it writes the output. And writing the output is the important thing about then doing the profiling from the submit jobs, because they just go and they run on the compute, and then we need to be able to find those after. Okay, and then finally what we can do is, this is an example here that interactively, once I've generated a bunch of test jobs that did performance and tested the output of those test sbatch jobs, I can either look at the outputs locally from the SSHFS share, or what I can do is I can log into the cluster on the VDI node and then interact with the output of those directories on the cluster storage system itself. So this example I'll show is basically on my local machine. I'll start up the VNC viewer, and then I'll go to the Graham VDI node, and then that will open up basically this desktop here where I can start Octave, and then I can go to the directory, load the files, and then check that the output matches what I was doing locally. So what I'll do is the demo. So now we'll get back to basically the overview of everything. I'm going to start off by doing my SSHFS comparison, looking at the data in MELD, and then I'll go over to a compute node, run some of those examples, I'll submit a batch job, and then I will look at it in the VDI node. So to do this, I will get myself a new terminal. Okay, so I've already copied the directory over to the cluster. Let's try that using the SCP. So the first thing that I'm going to do is I'm going to do an SSHFS mount. This is me at Compute Canada or the Alliance. I'm going to go through the Graham data transfer node #1, and then I'm going to mount my Scratch directory into the local directory that I have here. And should be going. And then the next one, I'm also going to mount the project copy that I have of that. Okay, so now that I've mounted these two directories onto my computer, what I can do is I can take a look at them using the MELD software that I have on my local machine. So MELD will basically put the local files that I have, and then beside it, it will show the remote mount of Scratch, and then the remote mount of the project. And we'll hit enter, and then this will start up MELD. It should appear somewhere. Right here. So what we have here is now, these are all the files that are in the Git repo that I'm using. We have these data files and the functions that I've written, as well as a couple of things for the repo. Now, what I can do is while I work remotely, I'll just be watching here. I'll be working in Scratch, and then new files will appear here. And then this is where I can interactively understand what I'm changing there. Okay, so now that that is done, what I will do is I will start an interactive job by logging into the cluster in another terminal. So I'll start the terminal here. Let's go to Graham. And I was missing at least one A. Add a couple extra characters. Now, where did I put that? So this is in sbatch. So I'm going to go over to the directory. So what I'm going to do here is, now that I'm in the remote system, I'm going to do a module load Octave. Module list. So see here that I have the Octave module loaded, and then I'm going to submit an interactive job here. And just need 1 hour for this one. So what this is going to do is, on my behalf, it's going to request a single CPU with 4 gigs of memory onto a compute node. And just wait for this to happen pretty quick. So this is the same thing as submitting an actual sbatch job, except instead of running the resources instead of running a specific program once the resources become available, what it's going to do instead is just send my terminal over to that compute node. So right now we can see that I'm here on the login node, and then once these resources are available, then this terminal will go on to the compute node. And of course, there it is. Okay, so just as I was going to try and do something else. So this became available, and what it did is it sent me over. Now this terminal is on the Graham 392 directory. In this job, it also brought over the environment. So if I do my module list here, you see that I still have Octave. And what I can do now is I can actually just start Octave. So this is now basically the Octave terminal on a compute node using the resources that I requested in that job submission. So in this case, now I can run that same profiling information that I did locally. And then we see here that I got a similar performance where if I didn't load the data first, did I? No, sorry, I didn't go to the directory. So I have to go to the directory. And where was that? It was in right. So in this directory, I can then run the analysis again. And then we see here that the single mean being subtracted from everything happened in 1.39 seconds. And then I can do the prof show and get back similar information. So this was a different procedure that I ran, where I think I computed the mean the same way every time. So this one still did do several sums, spent most of its time running that sum. So what I can do is I can try another one. In this case, it should calculate the mean first, and then it doesn't have to calculate the mean every time, and then it happens much more quickly. And then I can do prof show here, and then show that it spent most of its time doing the binary subtraction and sum. So this is now an example of just specifically running that process on a compute node, the same one that I was doing locally, the same process, but now just making sure that it performs the same way, given the parameters that I've requested in the interactive job. Now, I can quit Octave here. I can do other things. And then if I check this again and update what's happened here, I haven't created any new files, so everything still looks the same. Now what I'll do is I'll open up another terminal. I'll SSH over. And then I'll go to that Scratch directory. So now that I'm in this directory, what I'm going to do is start just submitting interactive jobs. So here I'm going to create myself a little submit script using Nano. And in that submit script, I'm going to run one of the functions that's created in this repo. So I'm going to submit this to my default account, just giving it 10 minutes and a gig of memory. And then it's going to add the path to my functions, and then it's going to run this submit, and then it's going to output the data files. So I'm going to save this. Yes. So now I've created this submit script. If I go back to meld and refresh this, I can see that in my Scratch space remotely, there's now a new file that doesn't exist locally or in project. And I can check out what that looks like here using meld software on my local machine. Let me take a look. Okay, so the next thing that I'll do if I want to submit jobs for profiling is I'll actually submit that job with that script, which will do this. And that somehow has the weird character I must have copied from presentation. Submit repmat. Oh, of course. That happened. Okay. So you got to name the file properly. This will submit the job. I see that I get this job ID. So this will be an actual interactive job that will run on a compute cluster somewhere. I can use saccount to check what's happening. So this job 4857194 is currently running. That's actually the interactive job that I see that I'm using in the other window. And then my current one is pending. And then if I want, I can keep sort of taking a look to see when this one will run. And I'm sure that it will run soon. Now, what will happen once that runs, I can go here and update, meld, and any outputs that are generated from that job will appear here. Now, in the meantime, what I'll do is I'll demonstrate how I want to then interactively work with the outputs, not locally on my machine, but through the VDI node. So I'll open another terminal, increase the font size, and then it's open the VNC viewer. So the VNC viewer will then, I'll direct it to the Grav VDI, Compute Canada, and then we end up basically getting the desktop where I can log in. Okay, so this is now desktop on the Grand VDI node. I can open a terminal here, and then in this terminal, I can use the module systems. I'm going to load the CC environment, the 2020 and GCC. And then I'm going to load the Octave module. Why module spider. Happens. So that now I have Octave loaded, and then what I can do now is I can request that this load Octave, which is similar to how I started it on the compute node. This is on a node on the Grand compute cluster, but this is not a compute node. This is a VDI node where we can do more interactive work. So this will actually open the Octave IDE. And what I can do is I can then just go to the directories that I know that I'm working in. And yes, I'll take a look whether this one has run, and it failed. So let's check out why it failed. Now, that job failed, and the way that I'm going to check on it is I'm going to update this, and I can see here that the output is here. So I'm going to run that, and then it's saying that the Octave command was not found. So that means that the space where I ran that job didn't have the module loaded. So I'm going to list them just to make sure that's the problem. That's definitely the problem. Load Octave 5.2.0. Make sure. And then what I'm going to do is I'm going to submit this job again with the module loaded. And I'm sure that everything will be fine. Okay, so that one is submitted. And let's see. And then it's pending. So we can wait for this one to occur. But basically, at the end of the day, with this one, I have access to the same data that I was running with locally. On the VDI node, it's not an ideal place to do the actual profiling performance. But if we want to work interactively without accessing the remote file system from my local machine, this is where we can run interactive things like the Octave IDE on a cluster that's basically on right with the remote file systems. So now we see that it's complete. Go back here. I'll update this one. And then the second one worked. So the slurm output of this one basically showed me that Octave started, and then it printed the output, which was just the output of the tick-tock during the performance. You can see that that ran in the Scratch directory. Nothing has been updated in project or locally. And then in my interactive instance on the VDI node, what I can do is there was another file that was output. So that batch job created an output file, which is a Matlab array of the resulting data from the mean subtraction. So what I can do is from here, I can load the output that was generated. These weird characters out of here. And then once that's loaded, I can do the visualizations that I talked about initially to check if the output, when I run this in a job, produces the same output. So now working interactively on the remote system, then we can do all of the checks that we want to see if everything is working the same whenever I do the performance test from a job. I think that is everything to demonstrate. And then, so finally, that was the demo. I started by doing the SSHFS. Then I submitted, or I logged into a job, did an interactive replication of what I was doing locally on a compute node. And then I did the profiling functions on compute jobs on other compute nodes. And then finally, with the output from that in the Scratch file system, I logged into the VDI node and then did the visualizations that I had been doing locally on the VDI node. And I think that's all that I wanted to get through in this one. So if there's any questions, still have a few minutes.